Thanks to Squarespace for sponsoring today's video. You have probably heard that modern day science believes the universe to be 13.8 billion years old. It seems rather unfathomable how anyone can come to that conclusion, but actually the how is not too difficult to understand. People just don't generally ask the question. Either they scoff at it or they accept it as truth. In this video we will explore this how, but also throw a spanner in the works due to the newly discovered age of one of our local stars, called the Methuselah star, which apparently is older than the age of the universe. So, 13.8 billion years old. How did we come to that figure? We currently see the universe is expanding and cooling. Everything is moving away from everything, excluding forces like gravity keeping things together. The speed of this expansion is known as the Hubble constant, and currently the universe is expanding at a rate of 80,000 kilometers per hour per million light years. So, the obvious conclusion from an expanding universe is that matter is becoming diluted. There's more space in between things. A less obvious result of the universe expanding is the stretching of light wavelengths known as redshift. What started off as extremely high energy and high frequency waves emitted soon after the Big Bang have become stretched, finally reaching us as less energetic microwaves, known as the cosmic microwave background radiation. It's also why the James Webb Space Telescope is an infrared telescope, as photons of light emitted by galaxies billions of light years away have had their frequencies shifted to the red so much that we need an infrared telescope to observe them. A photon contains energy, and a higher frequency wavelength means more energy, which means it is hotter. Lower frequencies mean it is less hot. Hence why we say the universe was once dense and hot, but now it's bigger but cooler. But how does knowing this help us work out the age of the universe? Well, we do need to assume a few things about the universe first. 1. The universe is uniformly dense on the largest scales. This seems wrong. It's clearly not uniform. There are superclusters full of densely packed galaxies, and supervoids containing not much at all. However, like stars in a galaxy, zoom out far enough, and suddenly everywhere looks the same. So we assume the universe is homogeneous. As a result of that, not only is matter distributed evenly, but 2. We also assume the universe's laws and properties are the same throughout in any direction. And 3. We assume the Big Bang occurred in all locations, everywhere at once. If you hadn't heard that before, you can check out my video about it here. Under the laws of general relativity, if these 3 things are true, then there is a connection between how old the universe is and how it expanded throughout its history. With these assumptions, we can get distance and brightness measurements between objects like stars, supernovae, and galaxies. For instance, white dwarf supernovae always appear about the same brightness. If an observed supernova is dim compared to what we expect, it is because it is further away. Finding out how dim tells us how far away it is, and thus how far back in time we are looking. We can also look for fluctuations in the cosmic microwave background radiation, which is a snapshot of the universe only a few hundred million years after the Big Bang. Comparing it to galaxy clusters we see today, there is a correlation, so we can see how it's fluctuated to understand how the universe evolved and expanded. Based on the expansion of the universe today, and how it did expand, we now know the universe is 68% dark energy, 27% dark matter, and 5% observable matter. But what is dark matter and dark energy? We really don't have much of an idea. However, we can see their effects. Dark energy is believed to be the driving force behind the universe's expansion, as the expansion would have slowed down by now without it. And dark matter is gravitational force we can't account for. Galaxies, and galaxy clusters in particular, seem to have a lot more mass than they should, meaning the gravitational pull is stronger. Dark matter is what must keep galaxy filaments together. We can observe its influence. In fact, we can even map out its mass distribution, like in this image. But we don't know what it is. We can't observe it. But for the purposes of this video, we don't need to know what it is, only what it does, to be able to work out the universe's age. So, we know the current rate of the universe's expansion, or the Hubble constant. We know how that redshifts light. We know the composition of the universe, and we know its properties. We can see how galaxies have evolved over time. We look for fluctuations in the cosmic microwave background radiation. We can use all of this together to extrapolate back to the earliest stages of the Big Bang. Using 3 different instruments, all looking at different aspects of the universe, all the answers have come back roughly the same, 13.8 billion years, with an estimated 99% accuracy. But there's another method, which has thrown a bit of a spanner in the works, and that is to measure the age of stars. Certain types of stars are very short-lived, going supernova in a matter of a few million years. Others could last for trillions of years. Not that we've seen one that old for obvious reasons. In fact, following the evolution of stars, we haven't really seen any older than about 13.2 billion years old. But this does mean that long-lived stars that formed as matter was coalescing shortly after the Big Bang would certainly still be around today. And this is where our friend Methuselah comes in. Methuselah is a metal-poor star, meaning it is very old and incredibly rare, and most special of all, it is only about 200 light years away from us, which means we can examine it relatively closely. Based on its evolution, it is an estimated 14.5 billion years old, give or take about 800 million years. This means it might have disproved the 13.8 billion figure. So, do we really know how old the universe is? Roughly. It wouldn't be surprising to see this figure change as our technology improves. We have the WFIRST and James Webb Space Telescopes coming out soon, with specific mission objectives to peer deep into the universe's past. Exciting times. Although, I don't think we'll see this figure vary than more than about 1 billion years in either direction. Research is still in very early days in this field, even if it has been a topic of research for a while. To be honest though, I'm so impressed we have got this far. Who would have even thought we could come up with any figure a few hundred years ago? All this may throw out more questions than it answered, but that is science in a nutshell, the ongoing search for truth. Thanks again to Squarespace for sponsoring this video. Squarespace gives people a powerful and beautiful online platform from which to create your own website. They have a bunch of features which you can integrate seamlessly into your own website, like their audio block feature to embed your podcasts or music with iTunes support, or something I find particularly useful, which is the ability to link various social media platforms to your website and embed videos. So, if you're looking to build a website, give it a go. If you use the link squarespace.com/astrum, you can try it out for free and get 10% off your first purchase. Thanks for watching. Don't forget to subscribe so you get more space-related videos in the future. And want to help pick the next Astrum Answers video? Become a patron or a member today. Links in the description. All the best and see you next time.